Kim, that was really lovely. Thank you so very, very much. And Merry, Merry Christmas, too. That was a lovely medley.
Oh, Merry Christmas and Happy Hanukkah, Happy Holidays.
Yes, happy holidays to everyone. Welcome to the December meeting of the Orange County Astronomers, everybody. We're really delighted you're here. And I think that we're changed over. Are we, Raisa? Okay. We have a really great program tonight to finish out the simply wonderful year that 2020 has been for all of us. We are, I think, all of us looking forward to better times in 2021. I hope all of you are staying safe and healthy, and that those of you who are in these geographic confines had a wonderful Thanksgiving, and those that were outside have had a wonderful celebration of whatever you do around this time of year. Anyway, without more ado, I think it is about time. Oh, actually, before I turn it over to the announcements, I would remind you that we do have an election ongoing. I know that's a bad term for many people right now, but if you haven't voted yet, we have an electronic option. If you have any questions about that, send an email to John Hoot. And we also have a paper option. So if you want to do it the old-fashioned way, there's a ballot in the Serious Astronomer, and you can also download one from the website. Just follow the directions. Put your name and address on the outside of the envelope, not on the ballot, and mail it to the address that's shown on the ballot. And one way or another, we will get the election underway and let you know what the results are come January. And without more ado, I will turn it over to Kyle Graham for the club announcements. Hi, Kyle.
Hello. All right, so I'm just going to get started here with the showing the website. Okay. So let me make this big for y'all. Okay, so here we go. This is the Orange County Astronomers website, ocastronomers.org. This is the homepage. You can find information about the next online general meeting here. And if you click there, it'll take you to the Zoom link. I'm assuming you all found that because you're here. So I'm going to move on. Big thing, we have the total solar eclipse that's coming up in the Southern Hemisphere on Monday. That is, there's going to be a live streaming event that from Chile. So you can take a virtual trip to Chile during this crazy year. So if you are interested in that, is on Monday morning at 6:30 to 9:30 a.m. bright and early. So if you want to see that, please click on this recent article link and I'll give you information about that. Moving further down the page, you're going to have your next upcoming events right here. If you click view more, that'll take you to the calendar, which I'll show more later. We're a member of Amazon Smile, so please participate in that program. It's a great fundraiser at no extra cost to you with your Amazon purchases, especially with holiday shopping coming around. Great time for that. And then the Orange County Astronomers shop, where it says buy a shirt, you can buy a variety of Orange County Astronomers merchandise right there. Next, we'll go up to the top and then to the calendar, which I mentioned earlier. Click on that button down below where the 3 next events are. It'll take you here too. You can see a month-by-month view. And for example, I can go to January, wherever. So, and then if you hover over the event, and it'll give you some information about it. And then if I click on it, it'll give me the detailed information, including the Zoom link now. Later, it'll say where it is once COVID is over, location, time. etc. Please note that if you are in if you're viewing us from outside the Pacific time zone, these times do not switch with you. They're always in the Pacific time zone, so just be aware of that. Next, we'll go to the special interest groups page. Cosmic Adventures is still a thing. If you're interested, you can click on that for more information. And then right here, we encourage everyone to join this OC Astronomers group. This email list is just the club email list where you can get all the information about what's going on in the club. So if you sign up for that, you'll be on the general email list. Then lastly, I need to move the Zoom square. If I click on contacts, that will take you to the contact page, and then you can see any club officer's email address along with group coordinators further down. Pretty much anyone you need to contact, their email is here. Emails are being checked regularly, and email is preferred, but if you do need to call, this number is being staffed throughout the COVID pandemic. So someone will pick up, and if they don't leave a message, someone will get back to you. All right, so now we're going to go to the slides. Here we go. So the announcement slides for this month. As Barbara mentioned earlier, we have the elections that are now in progress. If you want to vote, please, we encourage you to vote. You should have gotten an e-voting email in the last couple weeks. I did it. It was extremely simple. I highly encourage you to go that route. You literally click the button, takes you to the ballot, you make your selections, and then you just press submit. That's it. There's no crazy login thing if you have the email. Very easy to do. If you didn't get that email, or if you've lost it or something, go email John Hood at this email address and he will help you. And then, as mentioned, there will be a paper ballot in the Serious Astronomer if you do vote through that method. Here are the candidates. You're going to notice that there is only, the candidates, there's only one per choice, but we still really want you to vote to really be getting that reassurance that there is support for the board from the club members and that they support these members doing these roles. And we still highly encourage you that in future years, if you do want to run for any of these positions, please do run for them.
Hello, welcome new members. We hope you enjoy this amazing meeting we've prepared for you, and thank you for staying safe during this tragic pandemic.
Nice. So we can finish one. On January 1st, we'll be if you're not here, you're welcome to welcome first.
Okay, it's me again. Special interest group. This group is open to anybody under 18, and sadly, due to the pandemic, all our events are closed. So yeah.
Let's support.
Ceci, could you check your sound? You're not coming through.
That better?
Much better. Thank you.
Okay. Like, what is it? I had a microphone on. I took the microphone off. Okay. Did you not hear Paloma either? All right. Well, Paloma said thank you for everyone. Okay. So, hey, for the fire, Dr. Pennypacker is actually doing this remote spotting for fires that would need help from as many eyes as possible. So if you're able to do that, contact him directly, that would be amazing. And then Paloma was welcoming all the new members during this pandemic, and she wished everyone a safe times of the holidays. Outreach events. So at this point, there are schools asking for events. And because of the pandemic, we want to ensure that not only the students and teachers, but our volunteers are also safe. So we're doing it virtually. Now, any of you out there in the club who has the ability to do computer, satellite, with your telescope, that will be really great because it's all virtual. Contact Cecilia Caballero, which that will be me. And
Hello, my name is Galileo, and today the moon is going to be a winning present. Also done.
All right, so the Learn Scope program, they are, since there is such a large inventory, they are going to be selling some of the telescopes off. So if you want to learn more about these opportunities, please email the email address below. The Serious Astronomer, Dave Fisher is always looking for new articles of interest, articles, images, trip reports, which there probably aren't very many of those right now, but anything else that's interesting from these crazy times, please contact him at newsletter@ocastronomers.org. Again, due to the pandemic, members are still strongly discouraged from visiting the ANSA site. Because of the lack of social element to the announcements, to the meetings, sorry, we're having the open spiral bar. This is where you get to socialize with fellow astronomers, people that those interactions that you're missing because of this virtual format. So please join us at Saturday at 10 p.m. For that. Then on tonight's agenda, the What's Up presentation will be done by John Garrett from the Orange County Astronomers, and then the main speaker will be Dr. Joel Primack from UC Santa Cruz, and the subject is the State of the Universe report. Thank you.
Okay, John, the floor is yours for the What's Up presentation.
No, hi. Are you seeing my screen? I'm assuming you're seeing my
Yes.
screen. Oh, okay. Hi. Nice to be here. Thank you for letting me do the What's Up on this month. The first thing that I wanted to share with you is that tomorrow we have a conjunction of the moon and Venus that would look pretty good for people who want to rise early. And so that I got up just in time to get this picture from this morning. And so there's the Venus up high, and you might see, Venus just above the tree, and the moon up high in the corner. And this morning, that's what it was this morning. And then there's Venus. And by tomorrow morning, the moon's going to be a lot closer. So it may be worthwhile to get up and get a little camera shot of that. The other events that are happening this month, we've got 3 meteor showers. And the first one is the Geminids. And the Geminids are considered active between the 4th and 17th of December. But the peak is going to be the night of the 13th and the 14th. So you want to get up in the middle of the night, set your alarm clock for the middle of the night on the 13th. And I've read that you can see up to 100 per hour under ideal conditions. I've never had those ideal conditions, but we do have a sliver of a crescent moon this weekend. So that's a pretty good situation if you get out into the desert. Here's a Geminid meteor that I photographed several years ago. It's my only confirmed Geminid meteor. Our second meteor shower is the Ursid meteor shower. And so they're active between the 17th and the 26th, and they peak on the 21st, the 22nd, and the rate is about 10 per hour. So I'm not going to urge all of you to get out for that one for 10 per hour. But if you're out doing some photography, you just might catch one anyway. And so this was the case when I caught one, I think, in my front yard. And so I got that little Ursid about 4 years ago. It might not be an Ursid, but first thing I did was whenever a meteor looks like it's passing directly over a star, I take a close look and make sure I'm not being fooled. And in this case, always take more than one picture when you're shooting meteors, because you may need to compare it to something like this to verify that, okay, it was something that the star was not part of the thing that I saw in the sky. But I do always have to caution you when you're photographing meteors that there's more and more satellites that are looking more and more like meteors all the time. So always take a few pictures. And if your meteor continues in the next photograph, you know you've got a satellite as opposed to a meteor. But if you're watching on nights of meteor showers, or if you see the meteor, that's also a good way to know that you've gotten one. And then the next meteor shower, as in the early days of January, the quadrantids. And the quadrantids, I think, are named after a constellation that's no longer recognized, but they're active from the 28th to the 12th of January. And the peak is the night of the January 2nd and morning of January 3rd. And supposedly there could be, under ideal conditions, if you get out in the desert or something, 80 per hour. However, you will be competing with a fairly bright gibbous moon for that meteor shower. The big event that you probably all have been hearing about is the grand conjunction of Jupiter and Saturn. And here's a photograph I took last night from my second story balcony, and I used a 3-inch refractor that I used for most of my astrophotographs that I'll be presenting in this show. You can see Jupiter down there with its moons, and Saturn with its one moon that I think is Titan, though I didn't actually confirm that, but it looks like it's in the right place. You can even see a little oval shape to Saturn because of its ring. Now, this is the field of view you would get with perhaps a 10-power pair of binocular. And so this was last night. Each night they're getting closer and closer together. Here's the pair that I photographed with a camera wide field lens on December 3rd. And there's Jupiter and Saturn. And also I'm marking my horizon because I found that my horizon on December 3rd is very comparable to what an ideal horizon would be on January 21st. So anyway, we've got Jupiter and Saturn. And when I took the picture last night, they were probably about that close together. Within next week, they'll be a little bit closer together and moving just a little bit up. And on the 16th, they're going to be joined by a sliver of a crescent moon, which makes a very nice trio of objects to observe in the evening. Use that as your wake-up call to start getting out, finding yourself a good location that has a unobstructed low horizon if you want to get a good look at these a few days later on the 21st. On the 17th, the moon starts to exit the scene, but it's still part of the beauty of the early evening. And I also discovered that M75, a globular cluster, is very close to those objects. So I took a picture last night also of M75. Here is Saturn, and here is M75 taken with my 3-inch refractor telescope, the same one that I had just taken the picture of Jupiter and Saturn with, turned it just a little bit, and if it shows up with my 3-inch refractor, it'll show up very well in a telescope. So many of us will be wondering, should we bother setting up, what kind of telescope should we bother setting up for the event? But there's going to be plenty of other things to look at. If there's, you'll be able to see Jupiter and Saturn, possibly in one field of view, depending on the magnification of your telescope, but you can always bounce around to some of these other objects like M75. Anyway, the night of the 21st is going to be the two closest together. So that's going to be your best opportunity to see both in a telescope within the same field of view. However, you might get as good of a view the night before or the night after, and you might want to try because you never know what the weather is going to do. Anyway, M55, I noticed when I was reviewing where these objects were, was on the horizon on the 21st, and it's also where my higher western horizon is in my telescope. I mean, from where I live. So that's how I kind of knew that what I was photographing on December 3rd was comparable to how high these planets are going to appear above the horizon on the 21st. Now let's go on to, while this event that we're anticipating is taking place right near the constellation of Capricornus. So I thought I'd show a few other things that you might want to look at while you're setting up your telescope to look at this grand conjunction. You might as well check out some other things in the area. And a couple of them are, these are some NGC, New General Catalog objects. Sorry, losing my voice. The NGC 6822 is a galaxy that I thought I'd be able to get a picture of for this meeting, but it turns out I wasn't able to. But I was able to get a picture of 6818. And I like to do what I think of as assisted observing with my telescope and common digital camera, a common Canon digital camera that I put on the back of my telescope. And when I look for things like planetary nebula, I find that with a very short exposure, those things just pop out in the picture. So I find it very rewarding just to be able to catch them. And so in this case, NGC, what was it called? 6818 pops out as a little planetary nebula in this picture. And this is again taken with my 3-inch refractor. I took another picture with my Schmidt-Cassegrain, my 8-inch scope, and this is about how that planetary nebula looks there. Again, I'm going for the little green color. I love seeing those things. If you go a little farther up in these constellations, you'll see the objects M30, M72, and NGC 7009. M30, this is taken in my small refractor. So it's a globular cluster. If it shows up well in my little refractor, it will look really good in any scope 8-inch or larger. And here is M72, a bit fainter and a little more diffuse, but this is taken in my 8-inch scope. And then there's M73 is right near there, but it just seems to be a group of like 4 stars. And so I threw it in just because I got the picture. And then one of my favorites is, and this is really nice for this time of year, we have Saturn very close to this, and in Capricornus, I mean, just off to the lower edge of it. But we also have right above Capricornus, the Saturn Nebula, which is NGC 7009. So if anything goes wrong in your observing session and you're unable to see Saturn and all of your guests, socially distanced guests with masks, want to see something like Saturn, you could point them to NGC 7009, the Saturn Nebula. So I'd highly recommend that. Anyway, so NGC 7009 is right here, Aquarius, M72 here, and M30 here. And also there's a comet in this area. The comet is very faint. I was able to photograph it about a week ago, but on the 11th, which is tonight, it's about here. And by the end of the month, it'll be up there. But the picture, here's the comet I took about a week ago during twilight. So I was very limited on how long I could expose. And if you can't see the comet, there it is. It's probably a 10th magnitude comet. It's Comet Howell passing through Capricornus. And so those are some objects in the Capricornus. We set up and conjunction. And I thought I'd throw in that you might want to look at while you're not. There's you go up from Capricorn, the constellation Aquarius, and a globular cluster, a beautiful globe overlooked at star parties, but it's here. This is it in scope. Here's I don't know if you're seeing inch scope, and in my 8-inch M2. Helix Nebula is in this area, but a small telescope can bring it out with about a minute exposure. It bring it out even better, or even better images, which is something I haven't there yet. And then I thought I'd share to look at in the sky. There's so much. There's a whole universe of stuff out there, especially as to just end with a few things that are this time of year. East, you'll see in Cepheus, and Cepheus is a good look at a couple of these objects. Garnet star is, and there's another GC40, and star photographed in just a few sight in any telescope. Very cheap camera, but if I continue to look at it and bring it in.
Okay, looks like we're experiencing some disconnectivity from John. I'm hopeful that he will be back soon. We're waiting for John to reconnect here.
I think that's about to.
Okay, thank you. Thank you, John. Very informative and entertaining as always. Can you hear us?
Oh, okay. Apparently, no one can hear me.
Yeah, I can just hear you on the computer.
I guess I'm dead. I don't know what's going on here. That was the last thing I was going to.
All right, my dad's having trouble talking, but he's saying that his show is over, and that was basically the last thing he was going to say. So.
Okay, thank you, Emma. So I would like to thank John. Hopefully he will be joining us back soon. Very informative and entertaining as always. So salutations. Welcome to the December 11th, 2020 general meeting of the Orange County Astronomers. My name is Reza, and I'm the vice president of the club, reporting live to you this time from the library of the International Space Station. Before I introduce our speaker for the night, I would like to bring to your attention the ways in which you can interact with us. First, please find and click on the raise hand menu item. We're going to use this shortly to welcome our speaker. I'm going to pause for a moment here, making sure everybody knows how to raise their hands. Okay, excellent. Thank you very much. And the second way in which you can interact is the chat. Please use it to send us any comments you may have, as some of you have already. And third is the Q&A and or ask question. You can use it during and after the main talk to ask your questions from the speaker. Actually, our speaker tonight has devised his talk in 3 sections and is going to pause after each to take your questions, and he promised to stay an extra hour. So please do send us your questions in the Q&A. Our speaker tonight specializes in the formation and evolution of galaxies and the nature of the dark matter that makes up most of the matter in the universe. After helping to create what is now called the standard model of particle physics, he began working in cosmology in the late 1970s. And he became a leader in the new field of particle astrophysics. His 1982 paper was the first to propose that a natural candidate for the dark matter is the lightest supersymmetric particle. He is one of the principal originators and developers of the theory of cold dark matter, which has become the basis for the standard model picture of the structure formation in the universe. He has been using supercomputers to simulate and visualize the evolution of the universe and the formation of galaxies under various assumptions. please join me by raising your hand virtually in welcoming Dr. Joel Primack. Dr. Primack.
Thanks, Faisal. Would you like me to share my screen now?
Yes, please. The floor is yours for your presentation.
Okay. As Reza said, I'm going to be discussing cosmology, galaxies, and planets. And at the end of each of these sections, I'll stop for some questions, just a few in the middle of the talk after the cosmology and galaxies part. And then I can stay for quite a long time if needed to discuss things after the end of the talk. So cosmos. So the picture that you're seeing, which is the Hubble Space Telescope Ultra Deep Field, is beautiful but misleading because it only shows half of 1% of cosmic density. That's the only part that shines. The other 99.5% of the universe is invisible. This cosmic density pyramid represents all the mass and energy in the universe. The big bottom part is dark energy, making up about 70% of cosmic density. Cold dark matter makes up about 25% of cosmic density. We don't know what the dark energy and cold dark matter are, but we know a lot about how they behave. Atoms make up about 5%. The majority of the atomic matter is invisible. It's probably mostly ionized hydrogen and helium. In fact, we now have direct evidence of that from fast radio bursts. But the part that we are most familiar with, the part that shines, is this 0.5% that's made mostly of hydrogen and helium that came out of the Big Bang. All other visible atoms, what astronomers call metals, everything heavier than hydrogen and helium, is about 1/100 of 1%, 10 to the minus 4 of the density of the universe. That's less even than the contribution of neutrinos. But of course, it's very important for us because the Earth and we are mostly made of those heavy atoms. Let's look more at the part that we can see. So of course, this is based on the Great Seal of the United States, which is on the back of the dollar bill. And we've slightly added to that by identifying the lower part of the pyramid, which has about 99.5, which has about the fraction that's hydrogen and helium, the 5% or so that is hydrogen and helium of cosmic density. And the top little bit is all other visible atoms. That's the 100th of a percent. So that's all visible matter. And Novus Ordo Seclorum, the new order of the universe, is the motto on the Great Seal of the United States, the new order of things. So stars start out with hydrogen and helium, and almost all the helium in the universe was made in the Big Bang, just in the first few minutes. Only a little bit, a few percent were added by all of the fusion that's occurred in stars. So the first stars are made of hydrogen and helium, and all the other visible atoms are made in stellar processes, either in stars or in stellar explosions or in merging stars. So this is a new version of the periodic table of the elements, where our best understanding today as to how the elements are formed is indicated by the color in the square representing each element. We'll come back to that. Now, many stars in the early universe may have been much more massive than our sun in binary star systems with other massive stars. When these stars ended their lives, as supernovas, they became massive black holes. The Laser Interferometer Gravity Wave Observatory, LIGO, has now detected mergers of massive black holes and more recently of neutron stars. This confirmed predictions of Einstein's theory of general relativity that had never been tested before. You can think of the test of general relativity as being represented by the speed compared to the speed of light. So for example, the Earth goes around the sun at 30 kilometers a second. The speed of light is 300,000 kilometers per second. So that's a very small ratio. When two black holes are just in the process of merging, they're going around each other at essentially the speed of light, just a slight bit less than the speed of light. And the predictions of how that would look, the signals that we would get, are being confirmed in great detail. So what do those signals look like? Well, this is showing you what they look like. So this is from the first black hole merger that was detected 3 years ago by LIGO. In August of 2017, LIGO and the European similar observatory, Virgo, announced the discovery of gravity waves from merging neutron stars. And the fact that it was discovered by 3 different sites at 3 different locations allowed a very small error box, and it was possible to find very quickly which galaxy the event had occurred in. A postdoc at UC Santa Cruz, his last name's Kirkpatrick, was the first human to see the light. He had a list of about 28 galaxies that it could have been, and he just went through them by comparing what they presently look like using a remote telescope in Chile with images from the archive. And somewhere around number 15, he saw that there was an extra spot of light, and that was the electromagnetic signal from the merging neutron stars. That meant that we could then point big telescopes at it, and it became clear that an enormous quantity of heavy elements produced by what's known as the R process, the rapid process, had been produced, about 5% of the mass of the sun in a few seconds in that merging event. The amount of gold is something like 10 times the mass of Earth. So that's a very important, these merging neutron stars are a very important source of a lot of the heavy elements. Elements like europium, which is a rare earth, gold, thorium, and uranium. So in this periodic table, as I said, you can see that uranium and thorium are entirely colored orange. They came from merging neutron stars. There are other possible kinds of special events that could have produced them, but they're very rare. Notice also that europium, this is a lanthanide rare earth, is mostly about 90% produced by merging neutron stars, with a little bit coming from dying low mass stars. That means asymptotic giant branch. As I said, we're going to come back to this. It's going to play an important role when we talk about planets. So here's another way of representing that cosmic density pyramid. Imagine that the entire universe is an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter. But we don't see the ships, we don't see the ocean. All we see are, you can think of them as the lights on the tops of the tall masts of the biggest ships. Those are the galaxies, the visible matter that's shining and giving us the light that we can see with telescopes. And that's the modern picture of the universe. My wife, Nancy Abrams, and I have given public lectures and written popular books about this. And we call the modern theory the double dark theory, because it's basically a theory that the universe is mostly made of dark matter and dark energy. Two, dark meaning invisible, not radiating objects. So This is, every so often I'm going to show you a somewhat technical slide, and I'm assuming that at least some people in the audience want to see some of what's going on behind the scenes in these theories. So what's the secret of cold dark matter? So that's in this plot on the upper left-hand side. I hope you can see the arrow. So on the vertical axis, I'm plotting the amplitude of the cosmic fluctuations, delta rho over rho. Rho is the density, so this is the difference, the deviation from average density. And it starts out at about 10 to the minus 5. That's this dashed line. And this is when, as the universe expands, a given scale represented here by the mass in units of solar masses. So 10 to the 6 solar masses, 1 million solar masses, 1 billion solar masses, 1 trillion solar masses, and so on. The theory says that they all come inside the horizon at just about the same amplitude. That's called a scale invariant spectrum. Notice, though, that when the amplitude, when these fluctuations come inside the horizon, when the horizon is big enough to encompass 10 to the 6 solar masses, there isn't much growth in the amplitude of the fluctuations for a while. And so they pile up. The 10 to the 6 and the 10 to the 9 aren't very different, and the 10 to the 12 aren't very different. And it's only when 10 to the 15 solar mass halos come inside the horizon, that much material comes inside the horizon, it hasn't formed a halo yet, that you get growth that's rising linearly with the scale factor. So on the horizontal axis, I'm plotting the scale factor. That's 1 over 1 plus the redshift. That's the factor by which the universe has expanded. So here we're looking at 10 to the minus 4.5 or so. The universe has expanded by the inverse of that today. Today, the scale factor by definition is 1. So anyway, the net result of this is that there's this piling up of fluctuations on small scales and a spreading out on large scales. If you plot the fluctuation amplitude versus the mass, you get these plots on the right. And this is the characteristic cold dark matter spectrum. So George Blumenthal and I worked this out in 1982. And this figure was from a paper in 1983. And it was the basis of our paper led by George in alphabetical order, although I was the one who actually wrote most of the paper. So George Blumenthal, Sandy Faber, me, and Martin Rees. Martin is the former president of the Royal Society, and he's now Lord Rees. But anyway, back in 1984, Martin hadn't even been knighted yet. And so we used this as the basis of a theory of structure formation in the universe. We worked out how galaxies would look and so on. And we compared it with observations, and it was remarkably good. Well, let's compare this spectrum of fluctuations with observations today. Uh-oh.
You might try clicking on the slide.
Okay, so so this is the current situation. This is the prediction of cold dark matter, the dashed white curve. And those are the observations on many different scales, from little clouds of gas, the so-called Lyman alpha forest, to small galaxies, to big galaxies, to clusters of galaxies, all the way up to the whole cosmic horizon. And as you see, the agreement with the theoretical predictions is spectacularly good. So it agrees with the double dark theory. And this is the final data release from the Planck satellite. So this is the cosmic microwave background data. The wiggly upper curve here is the angular power spectrum. And what it shows is that the universe favors about 1 degree fluctuations. So this is the map of the whole sky, cosmic microwave background temperature. So 1 degree is favored, half a degree is disfavored. A third of a degree is favored, a quarter of a degree is this favored, and so on. The theory was worked out years before this data became available. There were small modifications of the cosmic parameters to fit the data, but once 6 parameters were adjusted to fit the data, you fit thousands of individual independent data points. So this is the temperature angular cross correlation. This is the temperature polarization cross correlation. This is the polarization angular power spectrum. They're all independent predictions, and there's simply no discrepancies. Everything is in fantastically good agreement with observations. And that includes smaller scale fluctuations in the cosmic microwave background that are being measured now from the ground, from Atacama Plateau and from the South Pole. So again, the agreement is spectacular. So does that mean that we basically know the basic history of the universe? Well, there's a fly in the ointment. There's a problem. The problem is that if you measure the expansion rate of the universe nearby, you get about 73 in our usual units, which are kilometers per second per megaparsec. And that's true more or less independently of the way you do it. Several of these independent measurements were based on what's called the cosmic distance ladder, where you're using various methods to estimate the distance to things. Perhaps the best known is this one up here, which uses mostly type 1a supernovae and Cepheid variables. But a completely independent method looking at the time delays in brightening and dimming of quadruply lensed quasars. In other words, where the quasar is seen 4 times. And quasars fluctuate a lot in how bright they are. And so by measuring the time delays between when one or another of these images get bright, you can independently measure the expansion rate of the universe. And again, you get 73. If you measure from the cosmic background radiation, fitting lambda CDM, standard modern, the double dark theory, you get 67.4. And you can use various early universe data, you get 67.4. Now, 73 plus or minus about 1 is 6 sigma away from 67. 6 sigma discrepancies don't happen by chance. There's something going on here. At least that's my feeling, and I think many astronomers are concerned about that. It turns out that there are several ways that the problem might be resolved, but the one that looks the best to me, you can ask me at the end why I like this one, but the thing that looks the best to me is something called early dark energy. So the idea is that there might have been more than the 2 episodes we know where dark energy played a very important role in the universe. One, cosmic inflation. That's a sort of super duper dark energy that very quickly disappears at the very beginning of the universe. And the other is the period starting about 5 billion years ago, when dark energy became a very important contributor to the cosmic density. And now, in fact, is much more of the cosmic density than anything else, about 70%. So the dashed curves represent the contribution of radiation to the cosmic density. 1 here is 100% of cosmic density. And down to about a redshift of 3,500, which is about 30,000 years after the Big Bang, the universe is mostly dominated, that is, most of the cosmic density is radiation. It's photons and neutrinos. But those very quickly die off, and matter takes over just about at that time, about 30,000 years after the Big Bang. And matter is the dominant component, nearly 100% of cosmic density. That's dark matter and ordinary matter, until fairly recently, a few billion years ago, when dark energy becomes most important. Basically, dark energy, if it's a cosmological constant, is just a property of space-time. And the more space there is as the universe expands, the more dark energy. But ordinary stuff, matter and radiation and so on, decrease in density as the universe expands. And that's why the dark energy takes over. Now, It turns out that having a little episode, represented here by the solid line, not the dashed line, of dark energy, producing a maximum of about 10% for a few thousand years, around 30,000 years after the Big Bang, is enough to solve the problem. This dark energy then disappears, and the universe is basically the standard double dark or lambda CDM universe, except that this has changed the scale of the universe a little bit, and it makes the Hubble parameter equal to 73, consistent with the early universe measurements. So that's what I'm showing over here on the left-hand side. The early dark energy solves the problem. So having seen that this was happening, I realized that no one had worked out what the consequences of this would be for the structure formation, for making galaxies and clusters of galaxies. So I got my old friend Anatoly Klipin and other people that I've worked with for years on this kind of thing to get together and do a bunch of supercomputer simulations. And what we found was that the prediction of this early dark energy version of lambda CDM agrees almost perfectly with standard lambda CDM today. But galaxies and clusters of galaxies form considerably earlier with early dark energy. For example, the number of clusters of galaxies at redshift 1 about 7 billion years ago goes up by a factor of 50%. And the number of galaxies, as you go up to higher redshifts, is increased by a factor of several. This has not yet been tested, but these things are going to be tested in the near future. For example, there's a very important satellite called eROSITA, which is doing an X-ray map of the entire sky, and it's going to have a catalog of something like 100,000 clusters of galaxies out to redshift 1 and slightly beyond. It'll also be a catalog of quasars and other active galactic nuclei. And James Webb Space Telescope is going to let us see galaxies out to higher redshift, and that'll be a good way to find out if the abundance of those galaxies is higher than standard lambda CDM. So our paper is on the archive. We have a favorable referee report, so it'll be published very soon. Okay, now I want to show you some dark matter simulations. And we do two kinds of simulations. We simulate very large scales where we just take into account the matter, basically the dark matter and the dark energy, and don't try to include the effects of ordinary matter. We then also can do hydro simulations where we do include the effects of ordinary matter. So the drunk on the says, quarks, neutrinos, mesons, all those damn particles you can't see. That's what drove me to drink. But now I can see them. And you're going to see the dark matter. But in order to make it possible to see it, of course, we have to use light. So everything that you see that's bright is, in fact, invisible dark matter. And the brighter it is, the denser the dark matter. So let's first of all look at the formation of a galaxy, but look not at the galaxy, just at the dark matter. Let's summarize. So it started expanding, expanding. But about halfway to the present, about 7 billion years into the expansion of the universe, the center has stopped expanding. And today, the universe is basically divided into two regions that in our popular books, my wife and I call tame space and wild space. So tame space just means space where gravity is holding things together. Gravity is not allowing it to expand. The local group of galaxies is an example of tame space. It's gravitationally bound. It's not expanding. And in fact, as I'm sure you all know, the Andromeda galaxy and our galaxy are flying toward each other. And in a few billion years, they'll collide and merge. On the other hand, things that are outside the local group are flying away from us faster and faster because of the effects of dark energy. So that's the important distinction on large scales. Regions that are held together by gravity and regions that aren't, which are expanding faster and faster. So higher resolution simulations produce images like this. This is from a simulation led by Volker Springel in Germany. And what I'm showing you here is how much larger the scale of the Milky Way's dark matter halo is than the visible Milky Way. So the Milky Way is about 100,000 light years across, but its dark matter halo is more than 1 million light years across. So the volume of the halo is about 1,000 times, more than 1,000 times larger than the volume of the visible Milky Way. That's typical. Galaxies, as we theorists think of them, are mostly empty space, empty of visible stuff, but full of dark matter lumps. And the bigger lumps are satellite galaxies. And we're discovering more and more of these satellite galaxies, and they're distributed essentially just the way the theory predicts. So this looks like a big success for the theory. Now, how does this fit into the really large scale structure on billions of light years? Well, something like this. So this is a little slice from one of our big simulations, the Bolshoi simulation, we call it, that we ran on NASA's Pleiades supercomputer, NASA's biggest supercomputer at NASA Ames Research Center in Mountain View, California. And what you see is how filamentary the distribution of matter is. Most of space, it has very low densities of matter. They're cosmic voids where there are hardly any galaxies. These little yellow dots are the dark matter halos that will host galaxies and groups of galaxies and clusters of galaxies. Let's look in more detail at what those look like. So what we're going to do is look at a region that's only 1,000th the volume of a big simulation like this. And incidentally, this is the smallest of our big simulations. We do simulations much bigger than this. But let's look at a region that's about 100 million light years across. So what I'm showing you now is just the dark matter halos that end up in that one big dark matter halo that will host a cluster of galaxies. The more massive of these dark matter halos has galaxies, and these are all falling together. Notice that most of these structures are quite elongated. They're prolate, meaning they have one long axis and two short axes. We also study many of the properties of every dark matter halo. So when we run these big simulations, we identify every single dark matter halo at every time step, and then study, we know the particle content, we know which ones have joined together to become bigger and bigger halos. That's called the merger tree. And so what I've just shown you is a visualization of the merger tree of one big halo. So what I just showed you didn't show you the expansion of the universe. The first video showed you the expansion of the universe, but now we're not showing you the expansion of the universe. And the reason is that if we tried to show you the expansion of the universe, you wouldn't be able to see what was going on until nearly the present. That's what we're doing in the upper set of figures. The lower set of 4 figures shows exactly the same simulation, but in order to see more clearly what's going on, we blow all of them up to the final size scale. We just expand them by multiplying by a factor that makes them all the same size as they are today. And all students who work in cosmology learn how to think in this way of visualizing things. We call it working in co-moving coordinates. Anyway, what I want to do now is show you the evolution of a patch of the universe this way in co-moving coordinates. Here's another simulation that we ran on NASA's. So we're now only a couple billion years into the universe, but look how filamentary they already look. Notice that the filaments are getting thicker. Things are moving down the filaments towards the densest regions, and the voids are getting empty. Okay, now we're just flying through. The simulation is finished evolving, and we're just honoring the views. So the person who first figured out why the universe is so filamentary is Jacob Zeldovich, a great Russian physicist and astrophysicist. And he showed mathematically that the phenomenon that produces these filamentary structures in the universe is mathematically essentially the same phenomenon that produces these sharp linear features at the bottom of a swimming pool in bright sunlight. That's the picture on the right. And so what happens is that you first get collapse in one dimension. It looks more or less like this. I'm showing my hands going together to make a pancake, or as the Russians would call it, blini. And then collapse occurs in a perpendicular direction, and that produces higher density, and that's what makes the filaments. And then collapse occurs in the higher density regions in a third dimension, and that makes somewhat spheroidal dark matter halos. So that's something that Zeldovich worked out in the 70s, actually, before we actually knew very much. So one of my students, Brandon Allgood, led this paper in 2006 that is still the basic paper on the evolution of the shapes of dark matter halos, the bound clumps of dark matter that host galaxies and clusters. So on the vertical axis of this graph, we're plotting the ratio of the short axis to the long axis. There are 3 axes of a triaxial ellipsoid. Let's call C the short axis and A the long axis. And what we're plotting is that ratio, short over long. And the closer that is to 1, the closer the object is to being spherical. But dark matter halos are almost never spherical. So the curves here are showing you the shape of the dark matter halo as a function of mass. And what you see is that the higher the mass, the more aspherical the halo is, the smaller the ratio is between the short axis and the long axis. And also what you see is that as time goes on, the halos become rounder, but still not very round. They're still, let's look at a Milky Way halo. That's 10 to the 12 solar masses. Today, the axis ratio for a typical halo of that mass is 0.6. So the long axis is considerably longer than the short axis. And halos of that mass at higher redshift were much more prolate. So if a halo has 1 long axis and 2 small axes, it's called prolate, pickle shape. If it has 2 long axes and 1 short axis, that's oblate. And of course, a disk is basically oblate. So the halos start out actually quite elongated, quite prolate, because they're forming along these very elongated dark matter filaments. As time goes on, though, the filaments thicken, as you saw in that video showing the evolution, and the accretion becomes more spherical. And so halos are more prolate in their inner parts and more spherical in their outer parts. That's going to turn out to have a lot to do with how galaxies form. So that's the end of the cosmic part of the talk. And as Reza said, I'm planning to stop for a minute to answer a few questions.
Thank you very much. So now Q&A is open for you to send your question. I already have a couple. Somebody's asking, when gravitational waves pass by, how much is the space compressed? Is this maybe less than a diameter of a proton?
Yeah, much less. It's about 10 to the minus 20. So it's a very, very small effect. And the only way we can see it is by amplifying the effect by a number of clever tricks. So for example, you bounce light back and forth many times between mirrors that are separated by a couple of kilometers. You also have to seismically isolate so that you don't get thrown off by passing trucks, let alone by earthquakes. And then also you demand that observatories, gravity wave observatories that are remote from each other, see the same gravity waves, but from the time delay, you can get a sense of what direction they're coming from. And the more of these we have, the better will be the ability to localize them in the sky. So we now have 3 of them simultaneously operating. The Japanese are about to come online, and then there'll be another one in India. So there'll be a total of 5 in a few years, and that'll give us a much better way of detecting. In addition, they're being made much more sensitive. So we're now getting, when they're on, LIGO and Virgo are detecting a few per week. And as they improve their sensitivity, we're probably going to get to the stage of detecting them more or less daily. So the amount of data that's coming in now from gravity wave observations is growing very rapidly.
Thank you. And we have another question from earlier in your talk. Somebody wants to make sure that you are discussing the temporal spectrums.
No, what I was describing was what's called the power spectrum of fluctuations. And I was showing you how that evolves with time. So what those curves were showing was the fluctuation amplitude on different mass scales. And then when I show you these plots that are sort of flat on the low mass end and steeply falling on the high mass end, that's the fluctuation spectrum at a given time, like today.
Thank you. And next question, are there globular clusters in the halo of the galaxy?
Not very far out. The globular clusters are there's basically 2 kinds of globular clusters, which we call them the trade, red and blue. The blue globulars are low metallicity globulars. They're very old, but so M92 is a classic example. And those are more or less spheroidally distributed, but on a length scale, a radius scale, not much larger than the size of the disk. In other words, about 10 kiloparsecs or 20 kiloparsecs. There are a few that are further out than that, but not many. But then there's the red globulars, the higher metallicity globulars, and those are much more distributed like a disk and very likely formed later. But the globular clusters are on a much smaller scale than the dark matter halo. The dark matter halo of a galaxy like the Milky Way has a radius of about 250 kiloparsecs. And remember, a parsec is 3.26 light years. So just multiply everything by 3 if you want to get it into light years. So the larger scale objects that we see are not globular clusters, they're satellite galaxies. And we've now discovered more than 50 satellite galaxies in the Milky Way, and new discoveries are coming in very frequently.
Thank
We've
you.
only looked at a small part of the sky. And so surely there are going to be hundreds.
Thank you. And next question, was dark matter created during the Big Bang?
Well, according to standard modern cosmology, there was an early process in the first tiny fraction of a second at the end of inflation that converted the energy that caused the super rapid expansion of the universe, inflation, into matter and energy, mostly radiation in the early universe, but also some matter. Exactly how that worked, we do not know. There are half a dozen different theoretical pictures, and we don't know which one or which combination are right. So that's a complicated question. That's called the reheating question after the end of cosmic inflation. And of course, it'll help if we know what the dark matter and the dark energy are, especially the dark matter. That may help to clarify how this process happens, but the short answer is we don't really know. I should go on now and take many more questions at the end.
Okay, sure.
So the next section is about galaxies. And to sort of put things in some kind of a context, let's look at the cosmic spheres of time. So this is another one of the pictures that my wife and I used in our popular lectures and in our books. The view from the center of the universe, and these beautiful color pictures are from our lectures at Yale, the so-called Terry lectures. And that was turned into a book by Yale University Press, which publishes beautiful color art books. So they did a great job on ours. So at the center is a galaxy like the Milky Way. As you look out in space, of course, you look back in time, because light that we get from further away left earlier to have time to get to us. And so that light was sent out by galaxies at earlier stages of their evolution. So the first sphere out from today is about 4.5 billion years ago. And that's when Earth formed and when the solar system formed. If you look at the galaxies out at that distance, they actually look very much like the nearby galaxies. But as you go out further to when big galaxies first started to form, about 10 billion years ago, the galaxies start to look pretty different. So all of those images between that sphere and where bright galaxies first start to form, about 500 million years after the Big Bang, those are images from Hubble Space Telescope from the ultra deep field. And they don't look anything like nearby galaxies. Look how long and clumpy and misshapen they are. We'll come back to that. Beyond that is the cosmic dark ages. We're going to be able to see a little further out into the dark ages when James Webb Space Telescope goes up, because it has the ability to see much further into the infrared. And so light that started out as starlight but got redshifted further and further into the infrared will be visible to James Webb Space Telescope. The beautiful colored sphere is the cosmic background radiation, and the color represents temperature. And the outermost sphere is the Big Bang itself, the cosmic horizon beyond which we can't see because light can't travel. You can only have light moving through the universe after the universe becomes electrically neutral. And that happens a few 100,000 years after the Big Bang. So that's when we get the light of the cosmic background radiation. We can, however, see gravity waves in principle from beyond that. So all the way back to cosmic inflation, possibly. Okay, well, that sets the context. Now, as time goes on, matter clumps together under the force of gravity as the universe expands, forming large structures. So in the background, we have the Bolshoi simulation, and then we're blowing up little regions. So this one is a galaxy, and the galaxy has a radius of about 10 kiloparsecs, about 30,000 light years. We're about halfway out in a galaxy, in our galaxy. Here's a blow up of a region where stars are forming, about 10 parsecs across. At the center of big galaxies, there are accretion disks of matter falling onto black holes, which blow out very strong emission perpendicular to the accretion disk. So all of those are things that we have to try to understand if we're going to understand galaxies. So here are two of the greatest discoveries that have been made in the last couple of decades about galaxies. One of them is plotting the ratio of the mass of the stars in a galaxy to the mass of the dark matter halo that's hosting that galaxy. And you see this curious inverted U shape. So what this is saying is that for galaxies like the Milky Way with a halo mass of about 10 to the 12 solar masses, you're getting the most efficient conversion of the ordinary matter, the gas, into stars. And you're getting about 0.03, about 3% of the mass of a big dark matter halo like the one that hosts the Milky Way. About 3% of its mass is stars. And that may seem surprising because remember, ordinary matter is about 5% of cosmic density and dark matter is about 25% of cosmic density. So the ratio is 1 to 5, 5 parts dark matter to 1 part ordinary matter. Or in other words, the ordinary matter is about 1/6 of the total. That's 16.6%. And 16% would be way up here. But the fraction of the gas that turns into stars is only a maximum of about 3% or a little over 3%. So galaxies are not very efficient at turning gas into stars. But galaxies are even less efficient if they weigh less or more than 10 to the 12 solar masses, if they're in halos that are larger or smaller. So if you go down to 10 to the 11 solar masses, it's more like 0.03%, 0.03%, 0.03 ratio rather. And if you go up to 10 to the 13, again, it's quite a lot smaller. So this is one of the crucial things we have to understand. Why does it work like this? We have a pretty good idea. We think it's supernova feedback on this end and supermassive black hole feedback, active galactic nuclei feedback on this end. The other thing that we've learned, starting about 15 years ago, is what's known in the trade as the main sequence of galaxies, of star-forming galaxies. So what's being plotted here is the star formation rate on the vertical axis and the mass, in this case, the stellar mass, on the horizontal axis. So the Milky Way is right around here, except that we're looking at today, and today would be down here. Now, what you see is that to a first approximation, the star formation rate grows more or less linearly with the mass, the stellar mass. And at higher redshift, the multiplier is a little bit higher. At lower redshift, it's a little bit lower. And this is basically because the universe is running out of gas that's dense and cold and can form stars. So most of that star formation that produces these galaxies didn't happen recently. It happened billions of years ago, peaking about 8 or 10 billion years ago for most galaxies. We call this the main sequence because what it's basically saying is that the single most important thing to know about a galaxy is its mass, either the stellar mass or the dark matter mass, because from this curve, if you know the stellar mass, you can convert that into dark matter mass. So that's a lot like stars on the main sequence, right? If you know the mass of a star, as long as it's still burning hydrogen in its core, you know a great deal about how bright the star is, what its spectrum looks like, and so forth. Because stars' evolution is governed by the mass. So it turns out it's the same story for galaxies. To a first approximation, the most important thing to know about a galaxy is its mass. Almost all the stars today are in large galaxies like our Milky Way. Nearby large galaxies are disk galaxies, like our galaxy, or big balls of stars called elliptical galaxies. Here are pictures of both of those. But most galaxies in the early universe didn't look anything like our Milky Way. In fact, the Milky Way didn't look anything like that back about 10 billion years and earlier. Most of them are pickle-shaped and clumpy. And you saw some pictures of those. We're just now figuring out how galaxies form and evolve with the help of big ground-based telescopes and Hubble and other space telescopes that let us see radiation that doesn't penetrate the atmosphere. So this is an astronaut installing Wide Field Camera 3. Hubble currently has 2 cameras. The Advanced Camera for Surveys, that took that ultra deep field picture that I showed you at the beginning, and Wide Field Camera 3. And the great advantage of Wide Field Camera 3 is that it has more infrared capability. So it has the same large field of view as Advanced Camera for Surveys, but it lets us see what galaxies really look like. What do I mean by that? All of these pictures that you see at the top of this slide are the same galaxy below and above. But if all we have is the Advanced Camera for Surveys, which basically just sees the light that our eye sees, for galaxies at redshift 2, about 10 billion years ago, we're just seeing the light that was ultraviolet then and has been expanded as the universe expands in wavelength to be visible and therefore something that can be seen by the Advanced Camera for Surveys. But when we can see the infrared light that started out as visible but is now infrared because of the expansion, we see what the galaxy really looks like. So what we're seeing is the ultraviolet light. That's light that's formed by very massive stars, O stars and B stars. And those stars don't live very long. So basically, you're just seeing where stars are forming if all you see is rest-frame ultraviolet. But when we can compare that with the rest-frame visible light, then we can see what the galaxies really look like. And of course, we actually have images where we have multiple wavelengths from Wide Field Camera 3 and also from Advanced Camera for Surveys. So we can put together images with up to 7 different wavebands typically. So this has been wonderful for allowing us to see what galaxies really look like. So what we're concentrating on with using Hubble is looking at galaxies from redshifts of 1, that's about 7 billion years ago, out to very high redshift, but especially this region that we're calling cosmic high noon. Cosmic dawn, we're just getting little glimpses with Hubble Space Telescope. James Webb is much better for that because it's a lot bigger mirror and meaning better light gathering, but also much better infrared capability. So why do galaxies have the shapes they do? I and most astrophysicists thought until recently that galaxies start as disks. Newton's laws explain why planetary orbits are elliptical, but not why planetary orbits in the solar system are nearly circular in the same plane, the ecliptic, and in the same direction as the sun rotates. Newton, when he was asked about that by one of his friends, said, "Oh, this proves God's handiwork." Well, the great French mathematical physicist Laplace explained this instead as a consequence of angular momentum conservation as the sun and planets form in a cooling and contracting protoplanetary gas cloud that forms a disk. Basically, this is just a consequence of angular momentum conservation as this gas radiates away its energy. It can't radiate its angular momentum, and that's what forces it to form a disk. And this is an actual image of a forming planetary system from ALMA, the array of radio telescopes on the Atacama Plateau in Chile. We actually have many, many examples. This is 20 examples of these forming planetary systems. Wonderful subject on its own, but not what we're talking about right now. And the point is that this is not what galaxies look like when they start to form. So for similar reasons, many astronomers thought that galaxies would start as disks, but Hubble's images of forming galaxies instead show that most forming galaxies are prolate, that is pickle-shaped. As we will see, this is a consequence of most galaxies forming in prolate dark matter halos oriented along massive dark matter filaments. So this is the abstract of a paper that a brilliant student, he was a senior on leave from Peking University, visiting us at Santa Cruz when he wrote this paper with me and several of my colleagues. And what we did was to analyze better than we had done before all the Hubble data that's available. And what we concluded is that for galaxies up to 10 to the 9.5 solar masses, they're mostly prolate. Even down to redshift a half, 40% are prolate. At redshifts of one and higher, a majority are prolate. Prolate meaning, again, pickle shaped. As you go up in mass, a smaller fraction, but still quite a large fraction, are prolate. And of course, most galaxies are these lower mass galaxies. So the vast majority of galaxies at redshifts of 1 and beyond, about 7 billion years ago and beyond, are prolate. Here's an example of one of these prolate galaxies. This is one of our simulations. So how do we know this? Because of course, we just see the galaxies as they are, however they're oriented on the sky. And the answer is, when you've got thousands of galaxy images, many thousands, you can see what the distribution of shapes is. And in particular, you can look at the axis ratio, the short axis length over the long axis length of the image, the two-dimensional image that our telescopes give us. Spheroidal galaxies always have a high axis ratio because it doesn't matter what direction they happen to be oriented, they're spheroidal, they're close to spherical, and so they're going to look round. Disk galaxies have to have a roughly even distribution of axis ratios from the ones that are face on, like this, to the ones that are edge on. If you don't see any large axis ratios, then that means that the galaxies have a much higher fraction that are this shape, and they can't be disk galaxies because you're going to see galaxies in random orientations. But prolate galaxies always have small axis ratios, except when you see them end on. So what does it look like when we actually look at the data? So this is, I don't know, about 20,000 galaxies. Every single point is a galaxy. What we're plotting, this is from our big Candel survey, the big survey using the cameras on Hubble Space Telescope. And what's plotted is the axis ratio, short axis over long axis on the vertical axis, and on the horizontal axis, the length, the logarithm of the length of the long axis. So long axis A, small axis B. And this is just the two axes of the image. So what you're seeing here is that there's an absence of high axis ratio. The upper right corner is pretty empty here too. And also this corner is pretty empty. And that's exactly what you expect if the galaxies are basically prolate. On the other hand, and this is the way this set of images, set of little panels has been set up, is mass increases to the right, galaxy mass. Redshift, time back in the universe, increases downward. And so galaxy evolution goes diagonally. That is, galaxies that are lower mass become higher mass as time goes on and still higher mass. So this is nearby galaxies. This is very distant galaxies. And here we see that, that this upper corner is about as populated as the lower corner. And also the color indicates how much attenuation there is of the light, how much more the red light gets through than the blue light. And you see that when we look at these galaxies with small axis ratio, they're very attenuated. And that's exactly what you expect if they're disk galaxies and you're looking through a lot of dust. You don't see anything like that at these higher redshifts at these earlier times. So this is telling us a great deal about how galaxies work. So we can compare to our simulations, and this shows one of our simulations. This shows the stars, the distribution of stars. The redder the color, the higher the density. and the white is even the highest density. And this is the dark matter. And you can see how the stars distribution corresponds very much to the high density dark matter. And also there's a filament which is going across this, and this dark matter halo and this galaxy is forming in the filament. If I had more time, I would actually stop now for several minutes and show you the evolution of this pickle-shaped dark matter and pickle-shaped stellar galaxy. We sometimes store thousands of time steps so we can make them. But I'm seeing the time is moving on. I've been talking for almost an hour. So let me skip that and just show you that the stars are very much oriented the way the center of the dark matter halo is. This is an edge-on view. This is an end-on view. And it's when the centers of the galaxies are still mostly dark matter that this is this dark matter dominated thing, that they're mostly elongated or prolate. And as soon as the center becomes mostly stars and not dark matter, then they're not prolate. So we have more detailed papers on this that we've done. So that's the way galaxies start out, these smaller galaxies. If you look at the more massive galaxies, the kind that host supermassive black holes, we see a very different story. And the basic story is we're plotting now the star formation rate increasing downward, and something that we're calling the compactness increasing to the right. So galaxies start out pretty diffuse, big, and this is after they're mostly pickle-shaped. They're higher mass at this point. But then what we see is that these galaxies appear to be evolving in the sense that they become smaller. We call these blue nuggets, although you'll see that they're mostly red. That's because of dust. And they evolve into what we call quench nuggets or red nuggets. And what's going on here? Is it really true that these stars are somehow ending up in a smaller structure in the center? And the answer is no, that's not what's going on. What's going on is that once galaxies get to be sufficiently massive, there are great inflows of gas into the center of the galaxy, and we get what we call starbursts. And that makes the center very, very bright. But massive stars, supernova, and very quickly this region is full of dust from those supernovas. And the result is that they become redder because the dust, just as it does in our atmosphere, takes out a lot of the blue light. So we see exactly the same phenomenon in X-rays. These are X-ray active galactic nuclei. This is the same kind of plot. Star formation rate increasing downward, compactness increasing to the right. And this phenomenon where the galaxies appear to get smaller, but really it's because the centers are getting brighter. And then eventually these galaxies accrete more gas and often end up as either big ellipticals or disk galaxies with big bright centers. So that we call the fast track of galaxy evolution. The Milky Way actually didn't evolve that way. The Milky Way was one of these slow track galaxies. And in our simulations, we see slow tracks and we see fast tracks. We see very much the same kind of thing that the observations are telling us. Let me not go into these details. So this is basically how the inner part of the galaxy behaves in the outer part of the galaxy. Let me just show you a video that shows you how this whole process works, but it's going to go by awfully fast. So what's being plotted on the upper part is gas, face on the left, edge on the right, and stars exactly oriented the same way, face on the left, edge on the right. You'll see why I'm calling it edge on after it goes. So this is one of these cases where we stored thousands of time steps so we can make these kinds of videos. And on the left-hand side, we're tracking the dark matter, the gas, and the stars, first in the center of the galaxy, and then at the lower part, and then on a larger scale. So this is the way these galaxy simulations look. And of course, to understand what's going on, we have to slow everything down and look at images, image by image, step by step. And we've done all of that. And so we have a pretty good idea how it all works. So this is showing you the main sequence of galaxy evolution. Remember, galaxies, as I told you, basically evolve with a star formation rate pretty close to proportional to the mass of the galaxy. So if we divide the star formation rate by the mass, it should be pretty close to constant. What actually happens in our simulations is we get oscillations around the center, but this is in logarithmic units. So 0.3 dex, that's 10 to the 0.3, is 2. Minus 0.3, 1/2. And so what this is basically saying is that for most of galaxy evolution on the main sequence, the galaxy doesn't get brighter than by about a factor of 2 or dimmer than by about a factor of 2 compared to the median. So this is really quite remarkable how galaxies really don't get that much brighter or that much dimmer than average once they're rapidly forming stars. However, after they've gone through a certain amount, so compaction, that's where gas flows into the center and makes it look like the center has become very bright. And then quenching, that's because the gas is used up or driven out by the supernova winds. But then more gas can flow in, so we sometimes have a second compaction event. But finally, the galaxy quenches, meaning it pretty much stops forming stars and gets lower and lower star formation rate and becomes an old red dead galaxy. So let me show you some images rather than read through all of this. So we used the latest machine learning technology to compare our simulations with the observations. And so this is an image from a press release that the University of California at Santa Cruz put out when we did this work. It's called Face Recognition for Galaxies. So if you just Google face recognition for galaxies, this all comes up. So this is what the galaxy looks like close up in this pre-blue nugget, or this is the compaction stage where a bright center is formed. This is what this same galaxy would look like to Hubble Space Telescope. It's a small telescope, 2.5 meter mirror. It doesn't have such great resolution, certainly not compared to James Webb or other bigger telescopes. But of course, it has the great advantage that it's above the atmosphere, so you don't have any atmospheric distortion. And you can see wavelengths that don't penetrate the atmosphere very well. So these are images from our simulations. And this is a real Hubble Space Telescope image. And this, of course, has background light, which we haven't bothered to put into these images that we make. These images, incidentally, take into account stellar evolution and also dust effects, scattering, attenuation, and so on. If you look closely at this one, this is one of these central nuggets. You can see that there's a hint here that this was a prolate galaxy, but the center has gotten so bright that you can hardly see these outer parts. And then after time goes on, most of these get more gas that comes in with high angular momentum, and it forms these beautiful disks. And this would be what a disk galaxy like this at redshift 2 would look like to Hubble. And this is an example of such a Hubble image. Let me skip this one. Basically, what this shows is that when we use the same deep learning code that we trained on our images to analyze all the Hubble Space Telescope data, all the images. And what we found was that the transition between the early stage, the middle stage, this nugget stage, and the post-nugget stage occurs at the same stellar mass as in our simulations. The only thing I'm going to mention here is that I'm showing you a comparison of the exact same galaxy in our simulation as Hubble would see it in its longest wavelength band, H band, and as James Webb Space Telescope would see it. Look how much more information we're getting from James Webb. assuming that James Webb, of course, everything works and it goes up. Currently, it's scheduled to go up in October of next year. We had, of course, hoped it would be up already. And the big delay is now largely because of COVID. So there are going to be many new observatories that are going to come online soon. So first of all, the survey I've been talking about is Candel's. That's the deepest survey of a fairly large region of the sky from hundreds of Hubble Space Telescope images in many different wavebands. The total area of all of these 5 fields, 2 northern fields, 2 southern fields, and equatorial field, is less than the area of the full moon, which is, of course, just half a degree across. The Cosmos field, 2 degrees by 2 degrees, is the largest region that's been imaged by Hubble, but not nearly as deep as the Candel's. James Webb Space Telescope, each little region that James Webb sees is like this little black dot. So very small, but quite wonderful. Somewhere around 2025, we hope, Nancy Grace Roman Space Telescope is going to go up. We used to call that WFIRST, Wide Field Infrared Survey Telescope. It's just been renamed after Nancy Roman. Nancy Roman, in each image, each pointing, is going to have an area 100 times the area of Hubble, and it's going to have the same light gathering power and nearly the same high resolution as Hubble. So each image with Nancy Roman Space Telescope is equivalent to 100 orbits with Hubble. But it's actually much better than that. Nancy Roman is going to be, Space Telescope is going to be at the L2 Lagrangian point, 1 million miles away from the Earth on the opposite side from the sun. And that means that it's not going to have the problem that Hubble has, which is it always has to avoid looking at the Earth or the moon or the sun. So it can only look in certain directions. A great thing about being out at L2 is you can see most of the sky and you don't have to keep slewing the telescope. So Roman is actually going to be not 100 times better than Hubble. It's going to be 1,000 times faster than Hubble. This really huge image is the Vera Rubin Observatory. We used to call it the Large Synoptic Survey Telescope. Now LSST stands for the big survey that it's going to be creating. And this is one single pointing with Vera Rubin Observatory. So this sees so much sky that every night it's going to image about half the southern sky. And it's going to revisit little sections frequently, several times per night. It'll revisit the entire southern sky every few nights. And so it's going to make basically a movie of the evolution of the universe. And what we're going to see is all kinds of short duration events, all kinds of transients. All the telescopes in the world, including amateur telescopes, find a few thousand supernovas per year. Vera Rubin Observatory will find 10,000 per night. Okay, well, very quickly, I want to move on to planets, but if people have a few questions about galaxies, this would be a good time. How am I doing on time? Is it okay if we take about 15 more minutes?
Yes, that's fine. I haven't had any questions for the galaxies yet here, so I think you can go on.
Okay, good. The planets part is going to be shorter. So most of the extrasolar planets that we found have come from the Kepler NASA satellite. And what Kepler did was to image a small region of the sky more or less continuously. And it looked basically at 150,000 stars. And what it was looking for was to have the starlight dim a little bit as a planet crossed the face of the star. Of course, most stars don't have planets that cross their face. And as a consequence...
Nancy or Nancy Holiday
hold on for just a minute. Hi, Nancy. I'm giving you a talk now.
What?
I'm giving a talk to the Orange County astronomers.
Okay. Let's talk in the morning then. Okay, sorry, both of you.
Okay, bye-bye. That's my wife calling. Okay, so anyway, many of you probably know that Kepler found about 4,000 extrasolar planets, and with other methods, we found another 500 or so. In some cases, we're able to do radial velocity and transiting observations. So Kepler only looked at a very small region of the galaxy, quite nearby, only about 3,000 light years away in a particular direction. Now, we used to think, before we started to get all this evidence on extrasolar planets, that our system is typical, with rocky planets near the star and gas giants further away, all in more or less circular orbits, all going around in the same direction as the star rotates. Well, it turns out that most planetary systems don't look anything like this. For one thing, they're a lot smaller. For another thing, those that are large, that have planets at 1 AU, the same distance as the Earth from the Sun, most of those planets are on quite elliptical orbits. It's very rare to find such large orbits that are so close to circular. So moreover, it turns out that most of these planetary systems have rocky planets that are considerably larger and more massive than our Earth or any of the other rocky planets in the solar system. On the scale of galaxies, there may be galactic habitable zones, not too close to the galaxy center where there are frequent supernovae and maybe outflows from supermassive black holes, accreting stuff, nor too far out from the center of the galaxy where metals, elements heavier than hydrogen and helium, may be too rare to form rocky planets. Of the 4,000 or so planetary systems that we've discovered so far, there are very few like ours, with all the planets widely separated in nearly circular orbits. And as I said, the most common type of planet seems to be 2 to 6 times Earth's mass, a super-Earth, or a little bit larger even, mini Neptunes. And of course, no such planet exists in our solar system. Some planets are in the habitable zone around their stars, which means that water would be in its liquid form during all or most of the lifetime of the planet. But most of these planets are probably not hospitable to advanced forms of life. For one thing, they might not have had an optimal abundance of the long-lived radioactive elements, thorium and uranium, to power a magnetic dynamo and plate tectonics. Too much thorium and uranium results in a lava world with frequent flood volcanism, the sort of thing that caused the greatest mass extinction here on Earth. Too little, and you wouldn't have plate tectonics, which recycles carbon, for example, on Earth, and has really helped to control the climate on timescales of many millions of years. So our living Earth may be a rare Goldilocks planet with just the right amount of uranium and thorium. This is something that you may not have heard about before because we just discovered this. Our paper on this was just published in Astrophysical Journal, November 10th. I sent Reza links to the article, and there have been a fair number of popular articles, including in Scientific American, that talks about this discovery that we made. So it turns out that because uranium and thorium are made by these very rare processes, merging neutron stars, for example, the amount differs quite a lot from planetary system to planetary system. And so Earth may not be at all typical. It may be that many planets have too much or too little, and for that reason would not be very suitable for evolution of complex life. So this is a picture that's supposed to represent Earth in the middle with a solid iron core, an outer liquid iron core, which is where the Earth's magnetic field comes from, with convective motions in the mantle driving a certain amount of volcanism and plate tectonics. That's Earth. If you have 2 or 3 times the amount of uranium and thorium, which many planets will, you have no magnetic dynamo and frequent flood volcanism, represented here with all these volcanoes. If you have less, you might have a magnetic dynamo, or maybe not, but you wouldn't have plate tectonics. which also is probably bad for the evolution of life. So this is a set of images that we made for the press release, and they've been repeated lots of places online. This is one of the plots from our paper. And what this shows is black is no geodynamo, no planetary dynamo, so no magnetic field. So if you just go up by a factor of about 50% from Earth in thorium and uranium, you lack a magnetic field for several 100 million years. Well, Earth never had a significant period when there was no magnetic field, as far back as we can tell, going back almost 4 billion years. And that's quite consistent with our calculations. But you just go up a little bit and you lose the magnetic field. You just go down a little bit and you probably lose plate tectonics. And nobody knew that because they hadn't appreciated that the amount of thorium and uranium. Incidentally, the thorium and uranium on Earth produce more than half of the heat of the Earth. The rest is just left over from the Earth's formation. So how can you tell if a planetary system is going to have the right amount or too much or too little uranium and thorium? Uranium and thorium are the two longest lived radioactive elements. And the answer is europium. Europium is more easily detected in stellar spectra than uranium and thorium. But it turns out that the abundance of europium tracks nicely with the abundance of thorium and uranium. That was checked by doing very detailed spectroscopy of more than 50 nearby stars. And the thorium-uranium linkage is very good. Of course, all of these papers are cited in our paper. The first author of our paper is Francis Nimmo. I'm the second author. And again, the references I gave to Reza so he can share them.
Yes, I'll put them on the website.
Great. So a little bit more about our planetary system. There's evidence that there was a late great bombardment of the inner planets lasting until about 750 million years after the solar system formed. It seems likely that there was a gigantic rearrangement of the outer solar system that caused many comets to hit the inner planets back then. Now, primitive microbial life got started on Earth only about 100 or 200 million years after the end of the late great bombardment. So primitive life may be very common in the universe since it started up so quickly on Earth. So at least in planets with liquid water in the habitable zone, there may very well be such primitive life. There are also moons in the outer solar system with liquid water under their icy surfaces, including Jupiter's moon Europa and Saturn's moon Enceladus. And here are some geysers that NASA's Cassini spacecraft took pictures of on Enceladus. They actually ran Cassini right through the geysers and collected some of that water. But nobody thought to put instruments on Cassini that could measure the spectra well enough to tell if there was organic molecules. So it's entirely possible that we don't have to drill down through the ice. In several of these planets, several of these moons, there are these geysers. And it may be that we just need to run a spacecraft through the geysers, collect the water, and see if there's any evidence of life in the warm water underneath the icy surface. So after primitive life formed on Earth, the stromatolites that we can still see in Australia and in the Caribbean, it took another 2 billion years for complex cells with nuclei, in other words, eukaryotic cells, to develop on Earth. And complex multicellular creatures only evolved about 500 million years ago, the so-called Cambrian explosion. So intelligent life and science only rose once on Earth, and so it may be very rare. New space observatories may make it possible for us to detect the effects of life on distant planets, for example, by atmospheric composition. We'll also keep searching for messages, and the huge square kilometer array of radio telescopes, thousands of radio telescopes being built across Australia, all the way out to New Zealand, and across Southern Africa, all the way to Madagascar, will help. So to conclude, without dark matter, we wouldn't exist. With only the ordinary matter, the universe would be a low-density, featureless soup. Dark matter started to form structures very early. Galaxies formed within bound halos, we call them, of dark matter. Stars formed in these galaxies, and stars made elements beyond hydrogen and helium, carbon, oxygen, nitrogen, and so forth. Rocky planets formed from some of these heavier elements. Life began and evolved on one such planet. So dark matter is our ancestor and our friend. Without it, we wouldn't exist. Science is much stranger than fiction. Before the discovery that most of the density of the universe is invisible, no one imagined this. What else remains to be discovered? Thanks for listening, and also I apologize for going a little bit longer than I had expected to. And I'm happy to entertain questions now.
Thank you very much, Dr. Primack. I see a lot of attendees, they're enjoying your talk and they're showing their raised hand as an applause. Thank you very much. That was a great talk. We now know what's going on, what's the state of cosmos, the universe in 3 scales, cosmos, galaxies, and planets. So let's go to the questions. And let me begin with a question of mine. So you mentioned that you have figured out that our planet, our solar system is not typical, contrary to what we thought. But am I wrong in my understanding that's because of, that's an artifact of our limitation on discovering planets as small as ours? So we can more easily discover large, huge planets that are closer to their star. So is that really the case, that they are more frequent, or is that just we could only discover
no,
those?
I don't think so. It's more complicated than that. If a planet the size of Earth, so first of all, Earth's radius is 1/100th the radius of the sun. It's 1/10th the radius of Jupiter. You can imagine on the picture of Jupiter, 10 Earths across the center and 10 Jupiters across the center of the sun. So that means that the volume of the sun is 1,000,000 times the volume of Earth. But what's relevant for Kepler isn't the volume, it's the radius. And as I said, the radius is 1/100th, and that means that the area that Earth obscures as it goes across the face of the sun is 10⁻⁴ of the area of the sun. So Kepler was designed to detect a drop in intensity of less than that, down to about 10⁻⁵. So if you have Earth-sized planets crossing stars the size of the sun, Kepler would see them. And a lot of the stars that Kepler actually looked at were smaller stars than the sun, which actually makes it easier. So that's actually not the problem. The problem is that as planets are further away from their star, the chance of having them cross directly in front of the star goes down, just for geometry. And also, to be detected as an extrasolar planet by Kepler, they demand that it be seen to have this light fluctuation drop 3 times. If they see it drop twice, that's pretty good. But a real confirmation is seeing the interval between the first and the second be the same as the interval between the second and the third. And of course, sometimes they see multiple planets. And anyway, so the problem is that the Kepler data was only for 4 years, a little less than 4 years before it ran into a problem. And so that means that planets that are further away, that have a year that's longer than Earth's year, would not have been detected because they wouldn't have had time to have 3 transits. Just barely 3 at the distance of the Earth. But you go a little bit further away than the Earth, and then Jupiter, for example, its year is 12 Earth years. It takes that long to go around the sun. Saturn, 30. And so we have to be patient to look at greater distances. However, again, by far the most common planets are these super Earths and mini Neptunes. Most planetary systems have super Earths or mini Neptunes. Ours has none. And moreover, most of the ones that we've seen are really quite small. We could have detected them much bigger. As I said, we can detect them out to at least an AU. Most of the ones we've seen are much smaller than that. The TRAPPIST system, for example, with 7 planets, would all fit inside the orbit of Mercury. So planetary systems are very different, and they're very different from ours.
Thank you.
There
Now
will be
that
some
puts
other
it
ones that are
into
like
perspective.
ours, but we haven't seen one yet.
Okay, excellent. So we have quite a few questions, and this one refers back to the first part of your talk. If gravitational wave detection is gaining ground in that it is a viable detection method, what are the next steps planned in for the technology?
Well, as I said, there's basically 2 things that are happening with LIGO type technology. One is that they're figuring out how to increase the sensitivity and also to do better seismic isolation. I actually visited LIGO Livingston in Louisiana, and I was given a behind the scenes tour. I went into the lab, saw all the stuff they're doing to improve it. And of course, they're sharing all the things they're learning with the other sites in Italy, the Virgo one, in Japan, and in India. So that's going to result in more frequent detections. And then, as I also said, having all these extra places where you can get time delays is going to give you much more precise localizations, just where on the sky to look. We have not yet seen an electromagnetic signal from merging black holes. It's not clear that we will. And for many purposes, what we want is to also get to see with telescopes the consequences of these mergers. And we may have detected a merger of a black hole and a neutron star. It's not completely clear. And those also are likely to be places that produce vast amounts of heavy elements. Anyway, there are other techniques. I could go on for some time on other ways of detecting gravity waves. One that you should be aware of is using the array of millisecond pulsar observations with radio telescopes. If gravity waves go through, they will slightly change the extremely precise timing of those millisecond pulsars. And that'll be a way. So we haven't seen any clear detections yet, but there are already useful upper limits. And of course, what we'd love to have is an observatory in space with a separation of not 2 kilometers, but several million kilometers. And that will be great for detecting mergers of very massive black holes. And that's called LISA. I was the chief cosmologist on the National Academy study on what we call the Beyond Einstein project. And we were told, this was 15 years ago, well, 2007, 2008. We were told that there was enough money in the NASA and Department of Energy budget to afford both James Webb Space Telescope and LISA. And the crucial thing was to test out the technologies in space. And the United States and the European Space Agency had combined efforts to do what was called LISA Pathfinder. However, the Bush administration pulled the rug out from under that. And the result was the US pulled out of LISA, at least the Pathfinder. The Europeans went ahead and all the technologies work. So there's no reason we couldn't, except for money, that we couldn't put LISA up to date. There's no technology that's needed that we don't already have. So I would really love to have the data coming in. Part of the problem was, I think, that we theorists were quite confident, and the people who build such experiments, that we could get these gravity wave observatories to work. But until LIGO actually worked and started producing this fabulous data, I don't think that the people with the money, Congress and the executive branch, we're ready to actually fund such things. And the Europeans also. They've now put LISA on their schedule, but not until the 2030s. But there's no fundamental reason why the US and the European Space Agency couldn't combine forces and make it happen on a much quicker timescale.
Thank you. So
on the other, let me just mention though, on the other side, the thing that in some sense is the most amazing is that our government and the European Space Agency and the Japanese, the Chinese, the Indians, etc., the Russians, they're all spending billions of dollars a year on space astronomy. And this is extremely good science, but it's not going to feed more people or solve the climate problem or anything like that. And so it's kind of amazing that we scientists have talked the governments into actually spending money to allow us to satisfy our curiosity about these things. It's quite a remarkable thing that the human race is doing. So, you know, we astronomers are hardly in the position to complain.
Thank you, yeah. So next question, somebody says that one would think Mars would have the same amount of uranium and thorium as Earth, since they were formed from the same material surrounding the sun in the early evolution of the solar system. But why are they, sorry, what was that again?
I was just saying that's right, yes. Mars should have essentially the same composition as Earth.
Okay, so and then why are they so different?
So as far as the heat is concerned, the crucial thing is the radius. The heat loss goes as the surface area, which goes as radius squared. The heat production due to radioactivity, given the same composition, goes as radius cubed, in other words, the volume. So a planet that's smaller radius, but similar density, like Mars, would have lost most of its heat a long time ago. So very likely in the early solar system, the first billion years, when the sun was much fainter than it is today, about 30% fainter. You know, stars tend to get brighter as they age, basically because the amount of helium builds up in the center, the sort of ash of the fusion. And so the center has to get hotter and hotter. And the consequence is that the star gets hotter. So it's complicated, but that's basically what happens. And so why is it that Mars appears to have had all this water, oceans, and all kinds of water events that we're now detecting by carefully studying the topography? And the answer is very likely that it was the radioactive heating from uranium and thorium, but also potassium. So potassium, potassium-40, has a half-life of about 1 billion years, uranium about 4 billion years, thorium 12 billion years. So for the first couple billion years, the potassium makes an extra contribution. And then it, you know, after 1 billion years, only half is left. After another 1 billion years, a quarter is left, and so on, you know. But in the early stage, the first 1 billion years or so, the radioactive heating was probably enough to make Mars have liquid water and so forth. There's a recent article that was just published that claims that, and it seems to me quite likely. Mars also had a magnetic field. We can tell that from rock samples, but it doesn't anymore. So Mars became a dead planet, pretty much. A little bit of volcanic activity, apparently, but and that's largely because of the radioactivity not being enough to provide the heating with a planet that's so small. You know, the surface to volume ratio goes up as the radius goes down, and it's a surface to volume ratio issue.
So then what about Venus? It's roughly the same size as the Earth.
Best guess on Venus is that Venus was too close to the sun and it lost all of its water. The water rises up to the top of the atmosphere, gets dissociated by ultraviolet from the sun, and the hydrogen is lost. And so why is that important? Well, water appears to be essential for plate tectonics. It effectively lubricates the continental drift. And if you don't have that, then you get what's called a stagnant lid planet, and that's what Venus is. And that also means that it makes it very hard for Venus to lose its internal heat. And that's why Venus doesn't have a magnetic field. So it also kills, you lose plate tectonics and you're probably going to lose the magnetic field. So, so that's our best guess with Venus, although we know less about Venus than we'd like to.
Thank you. Now, the next question, do we have a clearer picture of the flipping of the Earth's magnetic field and how that would vary with differing abundance of thorium and uranium?
The first part is, why does the Earth's magnetic field move and flip and so forth? And my Santa Cruz colleague, Gary Glatzmeyer, who's now retired, is the one who first figured all of that out. This was like 25 years ago. And his beautiful computer simulations were on the cover of Scientific American, Nature, etc. So Gary Glatzmeyer, Glatzmeier, and his model predicted the more or less chaotic evolution that we see on Earth. So other people have now done similar work and confirmed what Gary did, but that looks like the right explanation. Now, I don't know. I certainly haven't been involved in running such models for other planets. And Gary is, I think, now sort of out of the game, being retired. I'm retired also, but I'm still very active. Gary's a little older than I am. I don't know. I wouldn't be surprised if somebody's, it was kind of surprising to me that no one had worked out the consequences of changing the amounts of uranium and thorium on rocky planets until we did. I was the one who pointed out that there should be a large variation in the amount of uranium and thorium because it comes from these rare events. We only discovered that thanks to the gravity wave detection of the merging neutron stars in April of 2017. And so pretty quickly, I realized that made this an interesting question. And it turned out, Santa Cruz is the main center in the whole UC system for astronomy and astrophysics. We're the headquarters for University of California observatories. We build many of the instruments on the big telescopes. They're built actually on the campus at UC Santa Cruz. So Santa Cruz is one of the smaller campuses of the University of California, but it's a giant in astronomy. So, it's incidentally, the person who ran the Kepler program, Natalie Battaglia, she got her PhD at Santa Cruz, and she's now been on the faculty for a year and a half, and she's organizing an astrobiology institute, and she just got her first big grant, $5 million from NASA. So I'm part of that in my spare time.
Excellent. Very much looking forward to the stuff that's going to come out of that. So let's go to the next question. They want to know, what are your thoughts about the end stages of inflation? Do you think that things are going to slow down or they contract or?
Oh, you don't mean inflation, you mean of the expansion of the universe.
That's probably, yes, what they mean.
Yeah, so the problem is that we don't know what the dark energy is. And it's possible that the dark energy is just Einstein's cosmological constant. In other words, it's just a property of space. And the more space, the more dark energy and so forth. And that is a very good fit to all the data we have right now. But we only know what the dark energy contribution to the energy density of the universe was at redshift of 1, 7 billion years ago, halfway back to the Big Bang. We only know that to about 50%. In other words, we know very little. And so Michael Turner, a professor at the University of Chicago, coined this term dark energy. And that's possibly Michael's most important contribution to astronomy, although he's also an important theorist. Because by calling it dark energy, he basically got the Department of Energy interested in funding a lot of the research. So the camera for the Vera Rubin telescope, the LSSD camera, is the biggest camera ever built. It's 2.5 billion pixels. I showed you how big it is on the sky, that image. So that's funded by the Department of Energy. And the reason is that it's going to be crucial for trying to figure out what the dark energy is. The Dark Energy Survey was partly funded by the Department of Energy. The Dark Energy Spectroscopic Instrument, DESI, which is the next stage of the Dark Energy Survey, is partly funded by DOE. It's a combination of Department of Energy and NSF. So by studying how the dark energy may have changed in the past, we can tell if it's just a constant or if it's evolving. And if it's evolving, what we expect is that it's going to go away. It turns out that, well, I don't want to spend too much time on it, but I wrote some of the early papers on inflation. The way dark energy can be modeled is you have a scalar field, a field with no spin, that's not at the minimum of its potential. And the smaller the amount of dark energy, the longer it takes to fade away. And the amount of dark energy is very large today compared to the amount of ordinary matter, but the density cosmologically is still quite small. Anyway, let me not, these are all interesting questions. I could go on at great length. We should probably instead have some more questions.
So the next question is, how close are we to the observation of dark matter? Could that happen in our lifetime?
It could happen tomorrow. So we have lots of evidence. The problem is that the interpretation of the evidence is ambiguous. So for example, I think it's still quite popular to imagine that the dark matter is a WIMP, a weakly interacting massive particle. A very clever coinage, also due to Michael Turner, the guy who came up with this term dark energy, and one of his friends, Barry Steigman. So they're the ones who coined this term, weakly interacting massive particle, WIMP. They didn't invent the idea that the dark matter could be such a particle. I was the one who did that in our 82 paper, where we said that supersymmetry naturally explains why such WIMPs should exist. But I didn't have I wasn't clever enough to come up with that neat acronym. So if such is the nature of dark matter, we expect that these WIMPs would annihilate with each other. So it turns out that in supersymmetry, there's a quantum number, a multiplicatively conserved quantum number called R. R squared, so R is -1 for the supersymmetric partner particles, it's +1 for ordinary particles, and it's conserved. It's called R parity. And so that means that the lightest supersymmetric partner particle is stable because it's the lightest particle that has R negative and it can't decay into anything because R is conserved. But two of these particles can come together and annihilate and turn into ordinary matter because R is conserved multiplicatively, like parity, if you know anything about that. Anyway, the net result is that the theory predicts that where the dark matter is dense, like in the center of our galaxy, there should be lots of this annihilation. That should produce, among other things, gamma rays. And you can calculate what the flux should be of the gamma rays because we know what the density of the dark matter is in the center of the galaxy. We see exactly the gamma rays that the theory predicts. Not more, not less, but exactly what the theory predicts. So why isn't that telling us what the dark matter is? And the answer is that there are other explanations. It turns out that a spherical array of millisecond pulsars would produce the same kind of signal. There were some papers a couple of years ago that claimed evidence that, in fact, the gamma rays are produced by these millisecond pulsars. However, the people who wrote those papers are now backing off. They've discovered that their calculations weren't right. So that could revive this story. Now, I'm not an author of the papers on this. I did, author papers that originally proposed this kind of dark matter particle. Hooper at the University of Chicago and Fermilab. There's lots of people who are writing papers on this. That's just one example. To really nail down what the dark matter is, we'd like to see it three different ways. We'd like to see the indirect effects like this annihilation signal. We'd like to see a direct detection, and we're building super duper underground observatories. They're always underground to protect them from cosmic rays. So the US has one that's going to go into operation soon at the Home State Gold Mine in South Dakota. They had a little experiment there with 300 kilograms of xenon. They're now souping that up to over 8 metric tons of xenon. There's a similar experiment being built at the Gran Sasso laboratory in Italy, and a similar experiment being built in the biggest, deepest underground laboratory in the world, which is in China, and that's called the Panda X experiment. These experiments are 100 times more sensitive than anything we've had up until now. So they may very well see it. And then finally, we'd like to make the stuff in the laboratory. For example, at the Large Hadron Collider in Geneva. And the Large Hadron Collider is being souped up to run at 10 times the event rate that it was before. And that may make it possible to see the rare events that involve production. What we want to do is see exactly the same thing, the same mass of particle, the same properties of the particle in all three ways. If we do, we've discovered what the dark matter is. So experiments are underway. I mean, it's going to keep getting more and more sensitive. So stay tuned.
Very exciting. Looking forward then. Then
back in 1987, 88, I wrote the first article on how you detect dark matter, along with Bernard Satellet at Berkeley, who's still a leader in the field, and my former postdoc at the time, David Seckel, who's also a leader in the field. So of course, having proposed various dark matter candidates, we immediately set out to figure out how you detect them. And mainly the problems were just technological, figuring out how to build and operate the kinds of detectors you need. And we're now at the stage where we know how to do it, and we're doing it.
So excellent. Now we are running out of time here, but there are a lot of interest about that. Your latest paper on the Earth being another Goldilocks planet. Let me combine all those questions into one. And first of all, let me get a promise from you that you will come back to us and tell us about that paper in the future months. Second,
actually, what I'd recommend is that you invite the first author of the paper, Francis Nimmo. Nimmo is the guy who figured out why the Earth has the magnetic field that it does and why Venus doesn't and all that stuff. And when I pointed out at one of the first meetings of our astrobiology group at Santa Cruz that there was this likely large variation in the amount of uranium and thorium, Francis said, "Oh, I can do that. I just pull out my old model," and because he, was just modeling Earth, and he wasn't thinking. He wrote this paper in 2004, and he wasn't thinking about other planets around other stars. He wasn't even thinking about, he did write about Venus, but he didn't even work out the consequence for Mars. And now, of course, that we've pointed this out, there'll probably be a lot of people who realize that they should be doing these calculations.
So the question is, do we have a good understanding of what causes this higher concentration of thorium and uranium on Earth, and how rare is it in the universe or abundant?
Okay, so the answer is that people have run simulations of the evolution of galaxies like the Milky Way. And in fact, there's two competing groups that have somewhat different answers. One of the groups did the work partly at Santa Cruz. So those are the ones that we take more seriously. And one of my co-authors on the paper, Enrico Ramirez Ruiz, is a co-author. In fact, the first author on the paper that we cite is one of his former graduate students who's continuing to work in this field. So when you run these things, the crucial thing is that the number of these neutron star merger events is really quite low. We have a pretty good idea of what it is, even though we've only seen one with the gravity wave detection. And the reason is that we're pretty sure that neutron star mergers cause what's known in the trade as short duration gamma ray bursts. So gamma ray bursts are these bright, short duration bursts of high energy gamma rays that we detect both from space and to some extent, we're beginning to detect it with ground-based gamma ray observatories. And the gamma ray bursts are classified into short and long duration. Short duration means 2 seconds or less, and long duration means longer than 2 seconds, but they're hardly ever more than a few minutes. The short duration ones are almost certainly neutron star mergers. So we have thousands of them that we've recorded. So we know what the event rate is per galaxy per time. And the answer is a few per million years in a galaxy the size of the Milky Way. That's to be compared with core collapse supernovae, the kind that produce the oxygen and most other elements, most of the common elements. And those are 1 or 2 per century. So enormously more frequent. And so the result is that the common elements that those produce, or the type 1a supernovae that make most of the iron group elements, those are also about 1 or so per century. So those are actually quite common. And the result is that the amount of iron builds up with time, but so the ratio of iron to magnesium, for example, which is produced in core collapse supernovae, or silicon, that ratio grows with time as more and more iron gets produced. But the amount of silicon and oxygen and magnesium and so forth doesn't change that much from one system to the other. But because these neutron star mergers are so rare, it makes a big difference how close one of these or several of these were to the gas cloud that the sun and planets formed out of. So that's why you expect a fairly big variation. And in fact, Jill Nyman's paper, she's the first author of the paper that my colleague on our paper, Enrico Ramirez Ruiz, he's also a co-author. What they found actually, what they predicted was the same large variation that we see. And how do we know what the variation is? Well, we use europium. Europium has actually been measured now in several thousand stars. And so I actually pulled out the database and I worked out how common, what the distribution is. And it turns out that the 1 sigma is a factor of 2 up or down. So many stars and planetary systems are going to have twice as much, and some have 3 or 4 times as much. It's not unusual. Or a third or a fourth. And it turns out that even a 50% change makes a huge difference in the fate of the planet. So, and as I said, the tracer is europium. So by measuring europium in stellar spectra, you can get a pretty good idea of what the planetary composition is.
Excellent. Thank you very much. There are quite a few other questions, but I apologize to the audience that I have to forego them because for the interest of the time, we are just...
Happy weekend, everybody. Thanks for being such a great audience, and I'm glad you're so interested. I'm just delighted to see so much interest in these kinds of astronomical topics. Of course, this is something I've now spent most of my life thinking about, but it's wonderful that so many people are interested.
Great. And again, thank you very much, Dr. Primack. We all enjoyed this talk very much, and great. So I would like to end the meeting right now. Please do check out our calendar for our future meetings. We have quite a few planned, and with this, there should be a questionnaire already open in your browser. We would appreciate your time answering that in order to improve the quality of our meeting. And I would like to wish everybody a very happy new year, and see you next year on January 8th, if not sooner, for other events. Thanks, everybody. And
Reza, did you still want a few of us to gather afterward for a debriefing?
Yes, please do.
Okay, it's getting late, so I didn't know, but I'm willing to hang around a little bit longer if you like.
Okay, thank you very much. I'll try to ask the extra questions at the other meeting and relay that to the people.
Okay.
So thank you very much, everybody, and have a great time. Bye.